Okay, so we're going to talk about trends in the periodic table. And the first two trends we're going to talk about are atomic size or radius. And atoms don't have sharply defined boundaries, so you cannot directly measure the radius of an atom, but there are a couple of ways to estimate its relative size. The first way is to use X-ray diffraction. That's a technique used for solid structures. So you would shoot basically a cathode ray, a beam of electrons at a solid, very small solid, and as those particles pass through, it's going to refract and leave marks. And so these marks will allow you to figure out what this looks like. And so this is an example of an X-ray diffraction of chromosomes. Another way is to estimate the distance between diatomic nuclei. So di means two, and so these are going to be two of the same atoms. So hydrogen is one that is diatomic, meaning it has to exist in a pair. So if you're able to find the nucleus of these guys, then you can take the distance between the nucleus, cut it in half, and that gives you the approximate radius of that atom. This method is only going to work for your diatomic molecules because they have to be of the same size. There are 7 diatomic molecules: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. And you do need to know these. Know that they only exist in pairs. They're either going to be paired with something else or they're going to be paired with themselves. You cannot just have one single hydrogen floating about. It's either going to be with another hydrogen attached to oxygen to make water, or attached to a chlorine to make hydrochloric acid, or it'll be attached to itself to make H2 hydrogen gas. So atomic size will generally decrease as you move across a period. And that's because we're adding more electrons to the same principal energy level. The nuclear charge is increasing, so it's attracting those electrons. So your nuclear charge is positive, your electrons are negative. Since you're adding them to the same principal energy level, there's going to be an attraction there pulling them in closer, causing them to decrease. So if we start here with lithium, okay, lithium's going to have 2 electrons here and 1 electron, so there's not going to be a whole lot of attraction. But as you go further down the periodic table, here we have carbon. Carbon's going to have 2 on its inner principal energy level, and then 4 out here. So now we're building more of an attraction. It's going to start to pull in towards the nucleus. And then when we get to neon here, we have 2 on our first principal energy level, and then we're going to have 8 on our outermost. So now we have a lot of electrons being attracted to this increasingly charged nucleus. So that's really going to pull them in, and it's going to make neon slightly smaller than lithium. As you move down the periodic table, you're adding electrons to successively higher principal energy levels. So you're adding more and more layers. Your nuclear charge is also increasing, but now there's going to be more space between the nucleus and those outermost electrons. So the attraction is not going to be as high. And so as we move down, here's lithium. Lithium's going to have its 2 electrons here. Make that bigger. Lithium's going to have its 2 electrons here, and then it's going to have its 1 on the outside. 19 here is potassium, so there's 2 here, there's 1 all the way out here. There's not going to be a whole lot of attraction because these guys here in the middle are blocking this electron from being attracted to the nucleus. And then as we move down to rubidium, same thing. You have your 2 electrons here in the middle. You have your electrons here. There's only 1 electron all the way out here. There's not going to be much of an attraction because these guys are blocking it. So just make note of this. We're going to add these to our periodic table tomorrow in class. So your radius is going to decrease as you move left to right. Radii decreases left to right. Radii is going to increase top to bottom. Your nuclear charge is going to increase in both directions because as you move across the periodic table, you're adding more protons to the nucleus, so it's going to increase. As you move down, you're adding more protons to the nucleus, so your nuclear charge is going to increase. So this brings us to shielding trends. Shielding, you're blocking. So those electrons that are in the middle, sorry about that, are going to block the electrons from those nuclear forces, the attraction to the valence electrons. So it's going to be like a shield in between. So as you go across, your nuclear charge is increasing, your valence electrons are increasing, those inner electrons are staying the same. So as you're moving across, your shielding effect is going to decrease as you move left to right across the periodic table. So there's not going to be a whole lot of shielding here. Here's lithium again with its 2 inner, 1, 2 inner, 4, it's 2 inner, and then 8. There's not a whole lot blocking these guys from being attracted to the nucleus. There's not a whole lot here. There's just those 2 lonely electrons, that 1 ring. But as you move down the periodic table, your shielding is going to increase. You're adding more sublevels. There's going to be more space in between those valence electrons and the nucleus. So you have more space here that's going to block this guy from the nucleus here. Okay, it's not going to be as strong as an effect for attraction. So as you move left to right across the periodic table, shielding decreases, and as you move top to bottom down the periodic table, shielding is going to increase.